Hello friends, in the previous lecture we have seen physical adsorption and chemical adsorption. Now we are going to study one of the most important topic like factors affecting absorption of gases on solids. First one, nature of adsorbate. Second, nature of adsorbent. Third, surface area of adsorbent. Fourth, temperature of surface. And fifth, pressure of gas. Now coming to first point, nature of adsorbate. The liquefaction of gas depends on its critical temperature. Gases having high critical temperature liquefy easily and can readily be adsorbed. Second point, nature of adsorbent. The substances which provide large surface area for a given mass are good absorbents. Third point, surface area of absorbent. Absorption is a surface phenomena. More the surface area of the absorbent, more will be the volume of the gas absorbed. Fourth point, temperature of surface. Absorption is an exothermic process. Hence, decrease in temperature increase the process of absorption. Fifth point, pressure of gas. At constant temperature, pressure of gas increases, absorption also increases. Hence, the amount of gas absorbed is directly proportional to pressure of gas. We learn about application of adsorption. First point, catalysis. The solid catalysts are used in many industrial manufacturing process. For example, iron is used as the catalyst in manufacturing of ammonia. Second point, gas mask. This device is used for breathing in coal mines to remove the poisonous gases. The device consists of activated charcoal which absorb these poisonous gases. Third point, control of humidity. Silica and alumina gases are good absorbents of moisture. Fourth point, separation of inert gases. Different inert gases having different rate of absorption. Hence, their separation is possible by adsorption on activated charcoal. Last point, fifth point, fourth flotation process. Fourth flotation method is used in concentration of sulfide ore in metallurgical process. In this process, hydrophobic pine oil adsorbed on the surface of sulfide ore to form thick froth. It helps in concentration of sulfide ore. Now we will see catalyst. A catalyst is defined as a substance which when added to a reacting system increases the rate of reaction without itself undergoing any permanent chemical changes. For example, 2 molecule of KClO3 in presence of MnO2 that gives 2 molecule of KCl plus 3 molecule of O2. In this reaction, MnO2 is used as a catalyst. Now we are going to study colloids, a number of substances we use in our day-to-day life are colloids. For example, milk, butter, jelly, cream, and also useful material like cement, glass, rubber. Example of colloids, blood and soils. First one, blood. It is a colloidal dispersion of plasma proteins and antibodies in water. Second one, soils. Fertile soils are colloidal in nature, where humus act as a protective colloid. Next point, types of solution. On the basis particle of the substance, solutions are classified into two types. One, true solution. Second, colloidal solution. First one, true solution. A homogeneous, transparent solution is called as a true solution and the particle size is in the range of 0.1 to 2 nanometer. For example, aqueous solution of NaCl and sugar. Second one, colloidal solution. A solution which constitutes a dispersed phase of colloidal particles of the size 2 nanometer to 500 nanometer, and the dispersion medium is called as colloidal solution. For example, starch. We are going to discuss phases of colloids. Colloidal solution is heterogeneous solution and it consists of two phases, one dispersed phase and second dispersion medium. First one, dispersed phase, a component of colloidal solution which is present in small proportion, is called as dispersed phase. Dispersed phase is like a solute in a solution. Second one, dispersion medium, a component of colloidal solution which is present in larger proportion, is called as dispersion medium. Dispersion medium is like a solvent in a solution. Next point, classification of colloids. Colloids are classified in three different ways. First one, classification of colloids based on physical state. In dispersed phase, solid. Dispersion medium, solid. Then type of colloid, solid sol. For example, colored glasses, porcelain and paper. When dispersed phase, solid. Dispersion medium, liquid. Then type of colloid, sols and gels. For example, paints, cell fluids, starch solution. When dispersed phase, solid. Dispersion medium, gas. Type of colloidal, aerosol. Example of smoke and dust. When dispersed phase, liquid. Dispersion medium, solid. Then type of colloid, gel. For example, cheese, butter and jellies. When dispersed phase, liquid. Dispersion medium, liquid. Then type of colloid, emulsion. For example, milk, hair, cream. When dispersed phase, liquid. Dispersion medium, gas. Then type of colloid, aerosol. For example, fog, mist, insecticide sprays. And last one, when dispersed phase, gas. Dispersion medium, solid. Then type of colloid, solid sol. For example, fumes, stone, plaster. Second point, classification of colloids based on interaction or affinity of phases. On the basis of interaction or affinity of phases, a colloidal solution is classified as lyophilic and lyophobic. First one, lyophilic colloids. Lyo means liquid, philic means loving. A colloidal solution in which the particles of dispersed phase have a great affinity for the dispersion medium are lyophilic colloids. For example, the sols of proteins, starch in water, rubber in benzene, cellulose acetate in acetone. Second one, lyophobic colloids. The colloids in which dispersed phase have little affinity or no affinity towards dispersion medium are called as lyophobic colloids. For example, metal sols and metal sulfide sols. Distinguish between lyophilic and lyophobic colloids. In lyophilic colloids, first one, formed easily by direct mixing. In lyophobic colloids, formed only by special methods. In lyophilic colloids, it is reversible. In lyophobic colloids, it is irreversible. Third one, in lyophilic colloids, the particles are not easily visible even under ultramicroscope. In lyophobic colloids, the particles are easily detected under ultramicroscope. In lyophilic colloids, fourth one, these are self-stabilized. In lyophobic colloids, these are unstable and hence require traces of stabilizer. In lyophilic colloids, fifth one, addition of large amount of electrolytes causes precipitation. In lyophobic colloids, addition of small amount of electrolytes causes precipitation. In lyophilic colloids, sixth one, viscosity of dispersed phase much higher than that the dispersion medium. In lyophobic colloids, viscosity of dispersed phase is nearly the same as the dispersion medium. In lyophilic colloids, 7. Surface tension of dispersed phase is lower than medium. In lyophobic colloids, surface tension of dispersed phase is nearly the same as the dispersion. Third point, classification of colloids based on molecular size. Colloids are classified into three types in accordance with size of their molecules. First one, multimolecular colloids. The individual particles consist of an aggregate of atoms or small molecules with size less than 10 raised to 3 picometer. For example, gold sol. Second one, macromolecular colloids. The molecules of the dispersed phase are sufficiently large in size to be of colloidal dimension. For example, starch and cellulose. Third point, associated colloids or micelles. The substances behave as a normal electrolytes at low concentration and associated in higher concentration, forming a colloidal solution. The associated particles are called as micelle. For example, soap and detergent. Soap molecule has a long hydrophobic hydrocarbon chain called tail attached to hydrophilic ionic group carboxylate called head. In water, the soap molecules arrange themselves to form spherical particles that are called as micelles. In each micelle, the hydrophobic tails of soap molecule point to the center and the hydrophilic heads lie on the surface of the sphere. As a result of this, soap dispersion in water is stable.